them. One of them gets a little bit hard, and I'm just going to leave it. And then I'm going to make some general remarks about my graded ring calculations. So the two examples I want to discuss are Horikawa surfaces of general type, so S, the usual thing, PG equals 3, K squared equals 4, or PG equals 4, K squared equals 5. So I'm going to start with the first, because that allows me to set up a little bit of notation and so on. But basically it's the same. So we do this analysis of base locus of Ks. So let's do PG equals 3, K squared equals 4. So, there are 3 elements in the canonical class, 3 curves, and it's quite logically possible that they have no base locus. So the base locus, if the base locus is empty, then phi Ks S to P2 is a 4-to-1 cover. And there are basically easy methods of showing that phi lower star of OS, so this is a structure sheaf, is O, let me just write O for OP2, plus 2 couplers of O of minus 2, plus 4, plus a single copy of O of minus 4. Right? And then, it's straightforward from this to go to S is, or the canonical image of S is S44 in P11122. Right? So I need 2 new sections here, and then the product of these 2 new sections in there is already a generator, and so I don't need a new generator in degree 4, and you write down the equations you must have in order to make an algebra out of that thing, and you get that. So this is easy. The other possibility is that the base locus is 1 point, 1 transverse point, right? So this is case 1. Horikawa liked these Roman numerals. 3. Base locus is P1 plus P2, or base locus is a minus 2 cycle. So it could be a single irreducible curve with self-intersection minus 2. So both of these have the same. This is called 3 sub A. Right, and I'm going to describe what happens in this case and how you go from this case to this case. So these are sort of basically too hard for today. So my student Duncan Dix, around 1985, wrote a whole PhD on this subject, and basically it's still quite difficult. I don't really know a simple interpretation of this. I don't know why. I can describe the results easily enough, but the results depend on calculations, and the calculations are just blind calculations, no understanding of what's going on. Okay, so let me do this case too. So I'm going to leave most of this as an exercise, because it's a really valuable exercise. If you really want to understand graded rings on surfaces, you should do this exercise, and it might take you a day or two. Not easy. So the thing I'm looking at is if I take a general curve C in Ks, then it's passing through the base point P, and it's transversal. So this means that the next curve, the other curves in the system, the curves in the system between them cut out the maximal ideal of the point, and this means that the general curve there is a general tangent vector at the point, and any two of them intersect transversely like this. So if I look at Ks restricted to C, on the one hand this is degree 4, on the other hand it's got a base point. So this is P plus G13. And so this is an exercise or a challenge. And as I say, it's not an easy exercise, but it's a very, very valuable one. So R of this C with this Ks restricted to C is the ring of x1, x2, y1, y2, z in degrees 1, 1, 2, 2, 3, right, with equations given by the Pfaffians. I'm going to explain again, of a 5 by 5 skew matrix that I can write like this: 0, x1, x2, y1, y2, y1, z, z, a, b. Okay, so this is a 5 by 5 skew symmetric matrix. This is the element M12. This is the element M13, and so on. So this is going to up to M15 and down to M45. I'm not writing the diagonal elements or the anti-symmetric or the left hand, the bottom left. Right. So let me. This is the result of a long calculation that involves some tricky points, and I'm not going to do it in detail here. But I want to say how it goes. So if I take the thing I'm assuming. So the assumption is that Kc is, so Ks plus C, it's twice of this linear system. So it's 2p plus 2g13. Okay, so C is a curve of genus 5. It's non-singular because of what I said about the transverse base point. So this is the assumption. So it has a G13, and the general curve of genus 5 does not have any G13s. So if you look at the canonical image of a curve of genus 5, assuming it's not hyperelliptic, then there's a case which is it's the intersection of 3 quadrics, and there's the other case that it's trigonal. Anyway, before we get even to the canonical image, I can ask. So, I know that G13. So the curve is, like this. So it's not specially, that's not especially useful for calculating triple covers. They're sort of basically not as easy as double covers. However, there is something else I can do, which is to take, so this is the G13. So if I can take G13 plus 2p, right? So this is the same as, this is Kc minus the G13. Right, just by this formula, and so we know that so we can apply Riemann-Roch. Riemann-Roch says this is a G25. So it's a map of curve C into P2, so into C bar in P2, and so a non-singular curve C, a non-singular C5 in P2 has genus 6, right? And so this one has genus 5, so this is not this map, so the C bar has one double point, and the double point is a cusp, right? So if I have any curve of genus 5 with a G13, then I do the same construction, Kc minus G13, that gives a map to from C to C bar. And the C bar is a quintic in P2. This is a G25. This is just calculation in Riemann-Roch. And then well, the thing that's special about this is that this is the G13 plus twice the point. So my curve, my curve is not really like this. My curve is really, how do I draw it? Should draw it like this. Right, so here's the, this is C, I'm sorry. Sorry, it's impossible to draw this, but, right, so here's my curve C in P2. It's of degree 5, right, and if I take the lines through this point, then they have a fixed locus, which is this this point, the point of the normalization with multiplicity 2, and then the rest is a G13. Right, so maybe I should have drawn it like this. Right, so this is the G13. Okay, and if you blow this up, you get F1, and then, so here's F1, here's the negative section, which I'm going to call B. I'll probably regret it later, but I'm going to do it anyway. And there's the section A. So this is the standard picture of F1. It's got, it's a P1 bundle over P1. Right, and the curve C is in the linear system 5 times A plus 2 times B. I'm sorry, 5 times A plus 3 times B. Right, so this is P2. If I take the pullback of the lines in P2, that gives me this linear system. Well, it gives me the linear system A plus B. Right, the ones that contain B are just A. So that's the lines containing A. So A cuts out the G13. Right, so here's my curve. Looks like this. Right, but it has this interesting feature that it's tangent to B at one point. B is the exceptional maps to P in there. All right. So how is my ring going to be generated? So I look at RC and the linear system on it, which is P plus G13. Right. So I think of this one as being P1, with coordinates T1, T2, and I think of U from OC to OC of P. The standard, the trivial inclusion, the inclusion that doesn't generate at P. Right, and then so in here I've got x1, x2 with xi is u times ti. So the ti's, I'm thinking of the ti's of section of the G13. So just putting the u is saying, and these have the point P as, where they're allowed to have a pole and don't have a pole, or where they have a 0 if you want. Right, and then if I go to Kc, then of course I get S2 of these xi's. Right, but they they're just sections of 2G13, so they don't yet have this pole. So I can add in Y1 and Y2. These are complementary elements, right? And I can choose them to be proportional to x1, x2. So I can choose them to be, this f1 is p of. I can write it in lots of different ways, but in particular I can write it O of 2 plus O of 1, right? And then this guy here contains x1 squared, x1, x2, x2 squared, and this one here contains y1, y2, and I can choose them so that x1, x2, ratio x1, x2 equals y1 to y2. Here I could choose this to be the point x1 equals 0. and then y1 is also, so I'm going from 2G13 to 2G13 plus P, and then to 2G13 plus 2P. And I can think of y1 as being the one in here, or, y1 times u or something like this anyway, and y2 as being complementary. Okay, so this is straightforward stuff. Right, and then in the next degree I get this guy z, and I'm not going to attempt to tell you how to do z. I mean, I tried to do it this morning, and it's basically quite tricky. But then, so in degree 3, if I look at 3 times p plus 3 times g12, then I certainly get cubics in x1, x2, of which there are 4, and then I get xi, yi, yj, of which there are 4, but then there's -1 relation, right? Because so x1, x2, y1, y2 is equal to 0. This is a relation between these 4 guys, and so there must be a new element there, z. So in degree 4, we're going to find at least 2 relations. So I'm not going to explain how to do the rest of the calculation, because I said it's quite tricky, and so you need to analyze the equations of this f1 in P2, which of course are very easy, everybody knows them, and then how to write down the curve C inside the f1. So, if I write down the equation C in P2, I might choose coordinates x0, x1, x2, and write this as x0 squared plus x0 squared, sorry, x0 cubed times x1 squared plus x0 squared times x2 cubed, and then plus x0 a4 plus b5, or something like this, where these are in x1, x2. And then, if you pull this equation up to f1, they're not hyperplane sections. I have to multiply by either x1 or x2 before they become hyperplane sections. So it's sort of basically tedious. But anyway, you take equations. This is, we're doing completely explicit concrete mathematics, so you can of course find these things if you really want to. So A4 and B4 at some quartics in x1, x2, y1, y2. And they're sort of basically these terms, and I don't want to go into it. Okay, so so there's going to be another relation in degree 5 and 6, 1 relation each. So I've got relations 3, 4, 4. Right, so the relations are, there's a relation in degree 3 here, there's a relation in degree 4 there, another one in degree 4 there, and then 5 and 6. So I want to explain just a little bit about these Pfaffian equations. Right, so I've said this before, you've probably heard me say this before, but it's important and I want people to, it's the main trick I'm using. And I'm going to use it in the other cases as well. Right, so I'm in a polynomial ring, in a, let's say, graded polynomial ring, k x 1 up to xn, it doesn't really matter. So these are graded in funny degrees if necessary. So these Mij's are homogeneous. Right, and they're homogeneous of degrees that increase. So here the degrees are, these entries have degree 0, 1, 1, 2, 2, 2, 3, 3, 4, and 4. Right? And these degrees are chosen, these degrees must have the property that if I take any 2 by 2 minor, I get something which is homogeneous of a well-defined degree. Right? So I want the Pfaffians, but the Pfaffians are really like 2 by 2 minors. Right? So if I do this 1 plus 2, 1 plus 2, I get 3. 1 plus 3 and 2 plus 2, I get 4. 3 plus 3 is 2 plus 4. Right? So this means they're of degree some alpha I plus beta j. I'm not going to. You can do this systematically if you want to, but I'm not going to do it. Right, then the Pfaffian, I'm going to write Pfaffian I, J, K, L, and these must be 4 distinct. And they're symmetric under. If you permute I, J, K, L, then they go into plus or minus themselves. So I'm going to always assume that they're increasing. So this is M, I, J, M, K, L minus M, I, K, M, J, L, and then plus M, I, L, M, J, K. Okay, so the thing I'm writing here is I'm writing, I'm doing this. I'm sure most of you have taught this in linear algebra to first year or second year kids. When you write down the determinant of a matrix, you take product of all possible products of elements that are in different rows and columns. So we're doing the same thing here. This M12, except that because of the symmetry, M12 is also over here, M12. So I want to think of the M12 as being in this row, but he's also in this row. Right? So I'm allowed to do M12, M3, 4. That's sensible, because 1, 2, 3, 4 are disjoints. Right? But it doesn't make sense to M12 times any of those, or M12 times any of those. And so what's left is these. Yeah? And so this is a certain polynomial. Now, when you do ordinary determinants, you have a little formula for the minors of a matrix, and then you have Cramer's rule, which tells you how to find the kernel or co-kernel of a matrix as a ratio of minors. So there's something exactly the same happening here. So I want to say, if I do, and let me say, all of this is plus or minus 1, right? Times the whole of this. You can make it's easy to make, you can easily make a sensible choice. I just don't want to go into it. So I write, I can write for 1, for 2, for 3, for 4, for 5. This is the same as 2, 3, 4, 5. Right? So I think of this as a vector. This is a vector with 5 entries. It's a row vector of 5. Right? If I take I can also take the original matrix M. And the fact is that if I take this Pfaffian times M, I get identically 0. Okay, so what am I saying? I'm saying I take M12 times M23, M45 minus M24, M34 plus M25. Then I do similar thing with M13. So I'm going to take, an overall minus. I cross out these rows and I do M12, M1, and so on. Right? And I get something which is identically 0. And the reason for that is because what I'm really doing is I'm really doubling the row M12, M13, M14, M15, and then calculating a determinant. Right? If you calculate a determinant with repeated rows, then you get 0. So this is Cramer's rule. So I've got this 5 by 5 matrix. It's a skew-symmetric matrix, and the rank of a skew-symmetric matrix is always even. So this is 5. It can't possibly have rank 5. The most it can have rank 4, so it has a kernel. What is its kernel? Well, I've just told you this is the co-kernel. Also, M times transpose of this Pfaffian is 0. Okay. So what's happening? I want to take. If I take for I as the 5 equations of a subvariety in spec of this K of x, x1 up to xn, this ring, then the identity I just wrote down, the identity that I'm calling Cramer's rule, says that there are 5 syzygies holding between them. Right. So syzygies means I might in some circumstances take these 5 quantities here to be the equations of a variety, so they generate the ideal of a variety. In many cases that's a good thing to do, a sensible thing to do. They generate the ideal of a variety, but there are these identities holding between them. So the for i's are certain polynomials there, generators of an ideal, and this is an identity holding between them. So, let's just do a much easier example, e.g. 3 by 3 matrix. 3 by 3 skew matrix. Right? A 3 by 3 skew matrix is of the form 0, and then, so I'm going to write it all out in here. I'm going to write out F3 minus F2, F1. So skew symmetric matrix, and now I'm going to okay, so exercise. What's the determinant of the matrix? Right? So you're supposed to calculate that and say, aha, 0. right? So what are the 2 by 2 minors of the matrix? So, you know, for example, if I take this one, what's that determinant? Right? It's F3 squared. So the 2 by 2 minors, so in general, the 2 by 2 minors, the 4 by 4 minors of M are for I times for J. Right? So the matrix, if I take the adjoint matrix of M has got determinant 0, its adjoint matrix has rank 0, has rank 1, and so it's the adjoint matrix is just a product of two vectors, right? And so you can see this here. You know, if I want to calculate, so if I calculate, let's do the diagonal ones first. We calculate take this 2 by 2 block, its determinant is F3 squared. I take the square of that, I get F3, right? This 2 by 2 block, the determinant is F1 squared, so I take that. So the three Pfaffians, are F1, F2, F3. And if I take this and if I take F1, F2, F3, and I think of it as a row vector, and I multiply it by this matrix, I'm getting, for example, in the first place, minus F2, F3 plus F2, F3. So I'm getting 0. Right? And then F1, F3, the F1 hits there, the F3 hits there, I get 0. Right? So the same thing's this is the same thing that's happening. All the 2 by 2 minors are products of these, also products of these Pfaffians. So this is a case of a 3 by 3, a codimension 3 complete intersection. The codimension 3 complete intersection is a particular case of a Pfaffian. Right? And so what's good about these syzygies? Well, the syzygies hold the key to, you know, I mean, the syzygies, I haven't gone into it, but if we were doing coherent cohomology, the syzygies and the projective resolution give you the cohomology. But more important from my point of view, they also give you the deformation theory. So to make a flat deformation, I need to, so I'm really talking flat deformation of what? Of this ring, kx1 up to xn, divided out by an ideal. I need to make, to change the equations, the generators of I, and while maintaining the syzygies. So, you know, I'm sure you've all seen the definition of flat module over a ring. You know, it's saying that the tensor product is exact. But what it really means is that I take the generators of the ring, I take the relations holding between the generators. So I take a module M, take a resolution of it. So this is just choosing generators for M, finite of course, then taking P1. So this is the relations holding between the generators of M. Right? So in order to know that M is flat over any ring, you need to know that the relations that hold between the generators for the ring A are exactly the same, also give the generators over the, I'm saying this in a complicated way, I want that the relations holding between generators commute with base change. So if I do M and I get this, then what I want is that M tensor, you know, whatever it is. This is over A. I want to do this. right, and I want this to be P0 tensor B, P1 tensor B. Right, I want this one to remain exact. And this is just saying exactly that when I've got the generators of M and I take the relations between them, that if I just take the same relations and put them in an exact, put them in a sequence here, this sequence remains exact. So the P0 remains, the generators here, P0, remain generators of M, and the P1 here remain the total set of all relations holding between those generators. Right? So I'm not doing this formally, but there are lots of places where you can read this up. Okay? So the point is that when we use Pfaffians, the matrix M, the matrix M gives rise to the Pfaffians, right? And M already contains all the syzygies between them. Right. So I'm trying to explain this in sort of in words rather than in formulas. Right. So if we change the entries of M essentially arbitrarily, this gives a flat deformation.
You mean preserving the symmetry, of course?
Oh yes, of course. So the of the skew matrix M. Yeah. When I say essentially, it means things like I'm not allowed the matrix to go to 0. I want it to remain. I want the locus where it drops rank to remain the same dimension. But that's a very coarse assumption, and in particular it's true for small deformations. Okay? So here I've got the thing I was doing before. Right? So this was the equations. So this gives 5 equations of a curve C in P 1, 1, 2, 2, 3. Okay, and I told you the degrees of these guys, and this guy here has degree 0. So you're supposed to calculate in your head those equations. The first set of them, x1, x2, and so on. These are these are just the first 3 of these syzygies involving either elements from row 1 or elements from row 2. These are 0 times z, 0 times a, 0 times b equals 2 by 2 minus there. So that's just redoing the 2 by 2 minus. 2 by 2 minus the equation of this scroll. Right, and then I have the more substantial equations, and so those are the equations where I've eliminated this row or eliminated this row. And then I have more complicated equations. However, if I change the entry 0 to entry lambda not equal to 0, I'm going to put lambda in there. It's degree 0, so I'm allowed to put a constant there. Then the first equation becomes lambda z equals x1, y2 minus x2, y1. Right, so in other words, so I've got this curve C, I've got an interlinear system which is G13 plus a fixed point here, and this is in one half of the canonical class. Right, and I can just wiggle the curve C a little. I can go to C lambda, and then this C lambda has some G14, which is now free. And it's still, the whole thing's still Gorenstein. It's still in the half KC. Okay, so what's happening here? I'm saying I put lambda here. Right, so all of the equations change just a little. All of the equations, lambda times z, lambda times a, lambda times b, change just a little. They change by adding in this term lambda. Right, but in particular, it eliminates z as a generator. So this thing here eliminates z as a generator. Right, and so this gives me, just from the point of view of curves, it gives me the possibility of taking a curve with this base point and this funny set of equations and moving it to a curve which is, so with lambda not equal to 0, the curve C lambda has now has C maps to P1 4-to-1 cover. Right, and so but this is not finished. But now I can put in arbitrary elements into the matrix M. In particular, I can put in polynomials in K of now not x1, x2, but x naught, x1, x2, y1, y2. That's it. Right. So when I was writing things to this here I had, so you know, in what way is this not completely the general matrix? Well, it's not general matrices as y1 there and y1 there. So I could, for example, add y1 plus x naught squared. Right? And then I could write z plus x naught cubed. Or, you know, x naught times x1 squared. And here, this a, I can move this to a primed of x naught, x1, x2. Right? And when I do this, my curve C extends out in such a way that if I put x naught equals 0, I get back the curve C. So this defines C in x naught in P of now 1, 1, 1, 2, 2, 3. Right, and this has the property that, this is the canonical model, so it's okay to use the letter. So that x naught equals 0 is the section C. Right, and you know, basically we don't have to do any work here. The matrix holds the equations of the variety, and it also holds the syzygies. And so I'm guaranteed that putting in any old junk I want here, I will still get a Gorenstein ring with the right degree and the right canonical class. Okay, and then I can do both of these operations at the same time. I can do both. I can add the x naught to get a surface, and I can add a lambda not equal to 0 to get rid of the base point. Right. So in some ways this is really the ideal example. This is a case in which you can really understand everything using just this sort of easy algebra. This, I mean, you have to learn the algebra, but once you've learned it, it's very easy to use. And you know, all of this business about flat deformations, which in general is very complicated, is just handled in an automatic way by this matrix. Okay, so I might come back to the case at part 3 of these surfaces, which are much harder later. But I want to go on with the other Horikawa family, the more famous one. So, you know, when you start writing down codimension, here we're in sort of some codimension. This one here is 5, codimension 3. This is a surface. You know, the equations. So if I do this, for example, in a fairly general way, then the equations, although they're Pfaffians, they still become quite big. And if you actually want to calculate, for example, that x is non-singular, then you know you're much better off with computer algebra. And so, you know, I mean, it takes about 5 minutes when you know what you're doing to write a little computer algebra program that verifies that you can find non-singular varieties here. But at the same time, you know, the operations I'm doing are not arbitrary. They're giving general deformations. So, you know, codimension 3, we have this trick of using 5x5 Pfaffians, and it sort of works miraculously well. So let me go on to the, so I started this PG equals 4k squared equals 5 last time. And I'm looking at I'm looking at the curve C in the linear system Ks. And I'm making the assumption that Ks restricted to C has a base point. So it's P, and then it's got to be P plus 2G12. Okay, so I'm just repeating what I said at the end of last time. C is a curve of genus non-singular, curve of genus 6. It's hyperelliptic. Right, so I have this Ks restricted to C is a priori a G25. So it's trying to map C as a plane quintic, and I'm assuming it's got a base point. And so, according to Clifford's theorem, the only possibility is that the linear system is twice a G12, and that means the curve is hyperelliptic. And so, you know, you do the little arithmetic here. This is 14 branch points, 14 Weierstrass points. And they break up as P and then plus 13 others. And these are called P1 up to P13. And so I'm going to remind you, so to describe the ring R and of C and Ks restricted to C. Well, first I'm going to do R of C and P. So this is K of U, V, W, degree 1, 2, and 13, divided by a single equation, W squared equals F13 of U squared V. Okay, so here U is OC included into OC of P. V is a section of OC of 2P with poles at P. pole of order 2 at P, and W is OC embeds into OC of P1 plus P2 plus P13. Right. So here's the picture is something like this. So here is U. This is the hyperelliptic map F, and so here I have this downstairs. I have T1, T2 coordinates on P1, and here I have T1 equals U squared. Right, and then so there's F13 of U squared V, which has 13 branch points as distinct roots. Okay, so all that's very beautiful and very easy. Okay, and so now we ask, what is the ring of C, Ks restricted to P? And so this one here is 5P. So what we're supposed to do is take this ring here, that we understand quite well, just a hypersurface ring, and take in it only elements of degree divisible by 5. Restricted to C. Thank you. Right. And so this is generated by, so I need U to the 5th, U cubed V, U V squared, then I need V to the 5th, so this is of degree 10, these are of degree 5, 5, 5, this one's of degree 10. And then what am I going to do with this W? Well, W is of degree 13. I've got to use the W, otherwise I won't have the curve birationally. Right? But I have to multiply, I'm only allowed to use elements of degree divisible by 5. So I have to do U squared times W and V times W. Right, so these are called x1, x2, x3, y, z1, z2. Right, and so later on in the ring there are also elements like z1 squared, but they're going to be taken care of not as generators, but there'll be a relation saying what they are, right? And so I say that the ring is this. It's a polynomial ring with these generators divided by an ideal, and the ideal has got 9 generators. So the 9 generators are given by, so I'm going to write wedge 2 of matrix x1, x2, x2, x3, x3 squared y, z1, z2 equals 0. Well, I mean, if they're generators of an ideal, I don't need to write equals 0. Yeah? So, you check, for example, x3 cubed is x2 times y. x3 cubed is x2 times y. Right? We're doing toric, when we write down these relations, where the relations are toric, the relations are of the form one monomial equals another monomial. So they're defining a toric variety, a rather special toric variety, of course. There are a lot of coincidences here. Right? And then 3 more, and they're given by z1 squared, z1, z2, z2 squared equals. So what I'm supposed to do is take this relation here in degree 26 and make him into a relation of degree 30 for z1 squared. So this is going to be, I take u to the 4th times, if I call this relation f26. Right, let me just call this capital F26. We'll understand exactly what he is in a while. So I take this, so this is now a polynomial of degree 30, And so he's got to be, it's possible to express him in terms of x1, x2, x3, and y. Right? And so here there's u squared v of 26, and here there's here there's v squared of 26. Right? And you know, the interesting thing, and this calculation appears in many other places. There is a kind of slightly delicate point here that the way you render this is not the way you write this out. So I'm supposed to write this out, so rendered as polynomials of degree. So they're of degree 30 in the u's and v's, but they'll be of degree 30 divided by 5 in x, xi, and y. So the way you do this is not unique. It's unique modulo the relations, but what you actually write here will certainly affect whether or not you're able to continue the calculation. So I claim, lemma, I write S13 of u squared v. Right? So this is the set of monomials u to the 26, u to the 24th times v, and so on. I think you can all figure out what's going on. U squared v to the 12th, u v to the 13th. So you know, the general term, u to the 2i, v to the 13 minus I. So I say if I is greater than or equal to 3, then it's divisible by u to the 6th. And if I is less than or equal to 5, then it's divisible by v to the power of 8. Right? So the thing I'm writing is completely trivial. Right? However, it has a nice consequence. Therefore, the three right-hand terms can be rendered as so let me just do it here. Let me write it down. So I can write this as x1 squared a, x1, x2 a, x2 squared b, and then it's convenient to write minus x3 to the 4th b2, x3 squared y b, and y squared b. So there's a general game here which is called rolling factors. So I take some expression. So you know, if we think about this x1 squared a, right? Then it's divisible. It's divisible by the x1. And so in it, I can take x1 and replace by x2. So I can roll. So I can roll from x1 to x2. Yeah. So here I'm replacing x1 squared by x1, x2. And this means that, you know, this is how the syzygies are going to come from between the equations. Right, I'm writing down 9 equations to define something which is codimension 4. So there must be a whole pile of syzygies. In fact, there are 16 syzygies here. And we have to control these. Right? But I'm doing, there's a general thing here, which is a general game, which is called rolling factors. I'm taking some expression here, and I'm exchanging x1 goes to x2. Here I'm doing x1 goes to x2. I could also do x2 goes to x3 and so on, or x3 squared goes to y. right? And it turns out, because of this lemma, because the thing that I'm trying to roll is this terms involving f26. Right? Every term in f26 is either divisible by u to the 6th, right? And so when I multiply it by u to the 4th, I get x1 squared in it, or it's divisible by v to the 8th. And that means when I multiply it by v squared, it's divisible by v to the 10th, which is y squared. Right? So this lemma makes... I'll show. Right? I mean, this is miraculously compact way of writing the equations. Right? And if you've heard me lecture on this kind of topic before, you'll obviously be aware of the fact that I'm writing down something which has 3 terms. So it's not toric. It's not just binomial like these equations, but it only involves 3 terms. And if it's 3 terms, then you can hope to make it into a Pfaffian, into a 4x4 Pfaffian. Okay, so maybe we stop for a quarter of an hour. I don't have so much more actually. So should we stop here?